All right, so for the exam review, first thing is just some logistics of the exam. It is during class time on Friday, regular time, regular place. Um, it will be probably 10 to 12 questions if I'm guessing. It really just depends on how many I make conceptual versus calculation. And I usually try to, as a benchmark, write a test that if I did it, it takes me a quarter of the class time to do it. So the test should take me about 10, 12 minutes, so that you have four times that. You can bring a cheat sheet, and you can write whatever you want on the front of a 8.5 by 11 piece of paper for that cheat sheet. You can do equations, you could do practice problems, you can do concepts, whatever you want. But this stuff that's on the practice exam is exactly what you'll be given on the actual exam. And all this stuff up here is going to look, I think, identical. I don't think I'm going to need to change anything there. So I would suggest reading over this stuff before so you know what's on that first page and you can just hit the ground running with the questions. Um, I think that is it. Logistics wise, I am assuming people will be bringing their own calculators. I'll have a few on hand if you don't. So I think I have about five or six that I can let people borrow. But if you have a calculator, it's probably better that you bring it, both because you're familiar with it and because then I have more that I can use for people who don't have. All right, with that, what we're going to start with is the notes themselves. We're going to just recap and I'll point out what is most important for the exam. So I'm going to be crossing out some things and saying, you don't got to worry about that. But they are important for understanding physics. They're just not necessarily what I'm going to be testing over. So you may not want to mark them out in your notes, but you'll maybe make a note to say it won't be on the exam. Okay, so this stuff on the first page is just kind of setting up things. So just why we use the units we do, what they are defined in terms of. None of that is prioritized on the exam. It's possible that you will have things in kilometers and you'll need to convert to meters and maybe millimeters to meters, that kind of thing. But unit conversion in the sense of an hour to a second or a meter to a mile or anything that's not just one of these prefix type conversions, that I'm not going to emphasize on the exam. If it's on there, it's maybe like one thing and it's not meant to be the problem is requiring you to convert. It may just be a little tiny step in a problem or something, if even that. Sig figs we threw out the window a long time ago, but as a good physicist, you would use them, good scientist. It just in class, we don't always have time to be good scientists. So all of this stuff you don't have to worry about. Trig, if you don't know that you need to worry about trig by now, that's probably a separate conversation that we got to talk about. But the main things that we've used are the Pythagorean theorem, sine, cosine, and tangent, and then using inverse sine, cosine, and tangent to find an angle if we know two sides. So we mostly do that in terms of vector stuff. And so you're going to want to do problems that involve adding vectors, finding the components of a vector, finding the components of our resultant vector, or in the context of the actual physics, finding a total displacement, finding a net force, finding the components of velocity for a projectile, putting those back together. 1 second. Okay, sorry for the interruption. Okay, so we said the trig functions, Pythagorean theorem. inverse trig stuff, and that's the main stuff for chapter 1. So it's really when we use it in the context of what we do in chapters 2, 3, and 4 that we need that stuff from chapter 1. In chapter 2, the main thing really, so I'm going to skip down to it and then come back a little bit. The biggest part is your kinematic equations, so applying them. So examples like these, and then free fall, where it is still a 1D kinematics problem, but the acceleration for stuff in free fall is just this 9.8 meters per second squared down. Those are good to take a look back at. Okay, how you solve a kinematics problem like that is given step by step. It is make your drawing, and that drawing includes both where the object is initially and where it ends up. You don't always know the exact numbers or directions for that kind of thing, but you just need some sort of representative drawing. You need to label what your values are for the kinematic variables, if you can label them for if you can label them for both initial and final position, velocity, time, all that stuff, and that'll help you fill in your table that we use, and then that will let you realize which things we know, which one we don't, and which of these equations is going to relate all those things. So if that is still something you're working on, it might be good to have this in your cheat sheet to help you select which kinematic equation might be relevant. Okay, so kinematic equations is a big one. The derivation of them is not, but applying them absolutely. Okay, if we backtrack a little bit now, as far as this other stuff, position time graphs is the other bigger focus. So interpreting position time graphs. Can you tell me about the velocity of something by knowing its position time graph? And you can do that for the average velocity by finding the slope between 2 points on your position time graph. If you want to know the velocity at a certain instant, you need to find the slope at that instant. That's really only possible for us without using calculus if we have a section where the line is straight, the position time curve is straight, because in that case, the instantaneous velocity is exactly the same as your average velocity. In other words, the slope at this one point here is the same as between any 2 points along that line. So I won't ask you to draw a position time graph given information. You'd go the other way. You're given a position time graph and you want to glean some information from it. So something like that is not so relevant, and really this problem probably is not one you want to focus as much on when working on position time graphs. This is good. This is a good one because you're finding actual numbers for average velocity, and you could find numbers for the instantaneous velocity from this position time graph. And then there's the possibility of finding accelerations once you know that stuff. So if you have a position time graph like this, where your slope is constant, that means your velocity is constant, that automatically tells you no acceleration is happening in that interval. And then there's no acceleration in interval 2, there's no acceleration in interval 3. Accelerations are only happening in the in-between parts where we have to change from one velocity to another. So all of these things, right, these are the definitions or how we define these things. They're important insofar as they're used in the kinematic equations and in position time graphs. I don't expect to really ask you to define them, but it is good to know the difference between them. So average speed is distance over time. Average velocity is displacement over time. Instantaneous speed is if you shrink to a really tiny distance over a really tiny time, what is that ratio? And that happens to be the magnitude or size of the instantaneous velocity, which is if you take a displacement, shrink it to a really tiny displacement that happened over a really short time, and find that ratio. So these are good examples, and these are good because it's reading off information, qualitative. And then knowing what the relationship between velocity and acceleration is. If they're in the same direction, something speeds up. If they're in opposite directions, that thing slows down. It's just a general concept. Okay, so that's chapter 2 stuff. And then for free fall, you can always take your acceleration to be 9.8 meters per second squared downward. Anytime you see a ball being thrown, dropped, that's the only two things I can think of, then you can automatically take your acceleration to be 9.8 meters per second squared downward. Okay, chapter 3, the big new thing in chapter 3 is vector addition, and using that to look at x and y components of something, put those together, get a vector, that kind of thing. And so when we're solving those problems where we see, I don't know, a boat going east, then south, then northwest, those kind of problems, the first step is to try and draw those three bits of it. So this would be like east, and then this would be south of east, and this would be north of east. You put those together to get your overall trip, the resultant vector. And then once you've drawn the whole picture, that's when you start using the information to get numbers for everything. You find the x component of your first vector A. You find the components of your vector B, how far down to the right it goes. Find them for vector C, how much to the right and up it goes. And you put those together in that table sort of format, that's going to give you your components for your resultant vector, which could be total displacement, net force, lots of different things, depending on what we're looking at. It's going to give you those components. You put those together with the Pythagorean theorem. That's going to give you the magnitude, the length of this vector. You use some trig, you can find the angles with that information. Okay, so that's the process for vector addition, and I'll recap that and look at an actual example, but just to get ahead of it a little bit. That means that knowing how to add vectors graphically, like before even putting numbers to anything, is important because it helps you solve problems where you do put numbers to stuff. And so again, I'm going to jump down a little bit and come back. The way that we add stuff, the way we add vectors is with components. And that means taking a vector, breaking it into a horizontal and a vertical piece. And we can do it in this parallelogram fashion. We can do it so that's the parallelogram way. We can do it in this tip to tail fashion. It's saying the same thing. It's just sometimes tip to tail is a little bit easier to work with because it shows you the right triangles you need to kind of use Pythagorean theorem, trig, all that stuff on to find your components. Parallelogram makes that a little less clear because it puts one of the components on the opposite side of where we need it to draw the triangle. And so knowing how to find your components given your magnitude and direction, that's finding the components of a vector. You do that for things like projectile motion, find the x and y velocity components. You do it when you're adding vectors to find the total displacement. You break each vector into its x and y components. So that's super important. And then you need to go the other way. You take your overall x and y components, maybe that's your overall displacement. You found those by doing a little table, adding down the columns, what you get for these two things here, your x and y components overall. You need to use Pythagorean theorem to get the magnitude of that displacement and you need to use trig to get the angle. It's not necessarily always going to be cosine to get horizontal and sine to get vertical. It's just if our picture has AY, the vertical opposite our angle theta, then it's sine. And if it has AX adjacent, then it's cosine. If the setup is something different, like we have, this is our angle, that's our vector, and these are two components down and to the right, or down to the left, I mean. Or again, we could do it as the parallelogram way. So maybe I'll draw over in red if we did it that way. Either is a valid way of drawing those components, either the two red vectors or the two green vectors. But anyway, if I do that, then my AX is opposite theta. So it is, if purple vector is A and it has magnitude A without the hat, AX in this picture is going to be A sine theta, and AY is a cosine theta. So it just depends on where your components sit relative to the angle you know something about. And so this gives some practice finding components. I don't think for a lot of people, knowing whether a component's positive or negative is causing a lot of trouble. It's really the second part. So I'd say if telling whether something's positive or negative is not too bad, focus on the second part. And then we put that all together here. This is our process every kind of vector addition problem. We take our two vectors, we lay them out tail to head to draw in our resultant vector. That's the graphical vector addition. And then to actually put numbers to all those things, we take our vector, clean up a little bit. We take our vectors that we're adding together, in this case, A and B, X and Y components. So you need to find AX. In this case, it would be A cosine theta A in that picture. And that's positive for this particular example. AY is positive A sine theta A. B, it's in this picture, positive B cosine theta B, positive B sine theta B. And that'll give you, once you add down those two columns, your X and Y components for your resultant vector. That resultant vector could again be net force, could be total displacement, could just be you're asked to add three generic vectors. This is what you do regardless. And the signs come from which way our vectors are pointing, and so which way their components are pointing. Adding down the columns is what's happening in this bit. That's adding down this column. In this one, that's adding down this column. And that's going to give you your components for your overall or resultant vector. That's what you get down here once you add down the two columns. Then you're using Pythagorean theorem to find from those two lengths, Rx and Ry, what the magnitude of your overall vector is. So you take what's in that box and that box, you do square root of the first one's squared plus the second squared, that'll give you magnitude. And then for the angle, you're doing, depends on which angle you're asked to find, but if you're, say, asked to find that one, you can say theta is inverse tangent of Ry over Rx. So it would be inverse tangent of what's in the second box over the first box. And again, I recommend throwing out the signs when you're doing the angle bit and just looking at your picture to kind of help you lock in on what that angle is, because the calculator can mess it up. One like this is likely, but probably with two vectors. rather than 3 that you have to add together. 2D kinematics, we spent a lot of time just kind of building it up. So it's just about applying the 2D kinematic equations. And so any examples where we're doing that are good to take a look at. The general procedure is usually something like you're either given your initial velocity components or you're given the initial overall velocity that you get when you add them together. If you're given your initial components, you can go ahead and start filling in your table, one for each axis. If you're not, you got to take this initial velocity vector and break it into x and y components using cosine or sine. And then at the end, you may be asked to find final velocity, which is you find your final x and y components. You use Pythagorean theorem to put them together to get this magnitude. You use inverse tangent or another inverse trig function to find this angle theta. Maybe it just asks you to find the components. It just depends on what the problem's asking for. The general procedure is draw a picture, label it with your kinematic variables, fill in your tables based on that information, select the kinematic equations that are going to cover your bases for what you have and what you want to know, and then solve for what you want to know. Projectile motion is just more 2D kinematics. It's just a special case where you can automatically set AY to negative 9.8 and AX to 0. You can also automatically set whatever your final X component of velocity is to your initial X component. So if you're told one of them, you automatically know the other one because the X component, this one never changes. It's the Y component, the vertical one, that does. And so we marked out this before because it's really just substituting in that information into these 2D kinematic equations, but it seems like it's a little bit easier for us to approach it this way. Just start from your kinematic equations every time, fill in that your AY is negative 9.8 and your AX, if you need it, so on something like this, is 0, and then proceed from there. So mark that out and mark that out. Just focus on the AY, AX, and that the final horizontal velocity is the same as initial. Problems like these, also likely. So 2D projectile motion problem. It's honestly more likely than a generic 2D motion problem. And by that, I mean, you're more likely to have these situations where you can automatically assume AX is 0, AY is negative 9.8. Okay, if there's questions throughout this, you can stop me and ask. We will do practice problems, but we'll do that after we get through this. Are there questions on any of the note stuff so far?
No, sir.
Okay, and if you're typing them, oh
I
yeah,
just came into the call. What part of notes are we in?
could you repeat that for me? What was the question again? I'm not sure who just asked me a question. Could you repeat your question? Okay,
I have a question.
yes.
So with the projectile motion stuff,
Mhm.
like if we're asked to find height, like I'm confused, like what equation will we use? Because like we just marked out the projectile motion like formula.
So the reason I marked this stuff out is because I get these equations by starting from these equations. And so I don't want you to get confused and think that you're dealing with two different types of problems just because we could simplify the equations we had up above a little bit to get these projectile motion equations. Instead, I would just say, start with these equations and then use that AX is equal to 0 for a projectile motion problem, AY is negative 9.8, and so on and so forth. So your process would be fill in your table and then decide which projectile motion equation is going to get you to where you want to be with this. So part B is where I guess we decided that's probably the way to go. And so I filled out my table. I said, okay, I need Y, AY, V0Y, and I need to use those to find time. So I go all the way back up to these equations and find the one that has Y, V0Y, AY, and time. And I use that instead of using the projectile motion specific version, which is this one. Okay, you'd get the same answer either way, but I feel like it's a little bit easier to follow why we use certain values and stuff if we just stick with these. Does that answer the question?
Yes, sir. Thank you.
All right, any other questions? All right, then we will keep going with chapter 4. So in chapter 4, the main big thing is these types of problems later on. So one like this is a possibility. One like this one. So just problems where you're still adding vectors, but now those vectors just so happen to be forces. And so this part is exactly like all the other vector addition you've ever done. You just fill it in, you put your components in, and then the only other potentially new thing is that sometimes we don't know the magnitude of one of our vectors, the length of it. And so we just use our vector symbol that we chose, and then write this for the magnitude, that vector thing without the hat on it. And then that just becomes something that we're trying to find in the process of doing this problem. How we find things like T1 and T2 in this problem are we take what we get by adding the columns and then set those equal to, because of Newton's second law, mass times acceleration in each direction. And then we decide, okay, is this object accelerating in the x direction? If so, I can put that here, or maybe that's what I'm solving for, just depends. Or is it not? And if it's not, I can set the right-hand side equal to 0. And then in some cases, you have a little bit of both, like something sitting on an, or rolling down an incline, something like that. You would have with the x component, the component parallel to the incline might be present. The thing is accelerating along that surface, but it's not accelerating perpendicular to it. It's not leaving the surface. It's not falling down into the surface. And so we could set this one equal to 0. Just kind of depends on what your setup is. In this one, we set both equal to 0 because we want the ring not to move. It should have no x or y acceleration. In ones like these down here, we set x to 0, the x acceleration, because no acceleration is happening horizontally, but we may have acceleration vertically. And in this one right here, we set it was 0 because it's not accelerating vertically either. These two problems, or really this one in particular, is too involved to ask of you. But the process, me drawing my diagram, labeling it, drawing my free body diagrams, which you will need to be able to do that, draw free body diagrams, and using them to fill out my component tables. That process is a good one to kind of review. But a problem this complicated would not be on the exam. One like this is a little bit more likely, but I mentioned in class, it will probably be more asking about the concept related stuff, like that the normal force decreases as we make that incline steeper. And I'll save something where you have something going up a ramp for when we have friction stuff, because that makes the problem also a little bit more complicated, but by that time we'll be a little bit more comfortable with doing free body diagrams, finding these forces and things. So a full analysis like this for something on an incline, I'll save for exam 2. But again, the process of how we solved it, that's good to take a look back at. And so that's the main thing, those types of problems. Now let's backtrack a little bit and just look at any other little details that could be relevant. So, this stuff, not super critical. Did I really not say more mass is more inertia? Great job, me. But anyway, that's not super critical. But Newton's first law, what it states, that's a concept question. It says unless a net force acts on something, meaning you have some forces adding up to give a non-zero vector, they don't cancel each other out, then so if there is no net force, if the vectors do cancel out to give a net force of 0, the object continues to do whatever it was doing before, whether that was rest or moving at a certain velocity. It's going to keep doing it. If there is a net force and the forces that added up to give it don't cancel out, that is the jurisdiction of Newton's second law. So we'll come back to that. But Newton's first law says what happens when there is 0 net force active. The thing remains at rest or moving at constant velocity. And so in solving those problems where you're filling out the components and all that stuff, you would use that information. If you're told something's moving at constant velocity, that's telling you that the net force on it is 0. And that would mean in your table, you could, once you add up all your components, set them equal to 0 for something moving at constant velocity. So first law, this stuff, not super important. These cases of equilibrium, again, helpful for solving problems. Seeing that something's moving at constant velocity or is at rest tells you that the net force is 0, and that helps you solve problems. Inertial reference frame is not on there. Second law, it says that the more mass you have, the less that thing will tend to accelerate for a certain net force. The more net force you have acting on a mass, the more that thing will tend to accelerate. And so that second law summarizes all of that. But we mostly use it in this form, the two components of it. And then, again, free body diagrams, very important because they help you solve problems. So it's practicing drawing. Third law, concepts wise, it could be on there. It just says, I push on you, you push on me just as hard in the opposite direction. I pull up on the earth just as hard as it pulls down on me, that gravitational force. Those kinds of ideas, that whenever one thing exerts a force on another, that other thing exerts a force on the one thing. This is your step-by-step process for filling out those tables, doing all that stuff to solve problems using Newton's laws. It's not on there. The only thing for gravitational force would be potentially applying that equation. So you're given a mass, you're given another mass, you're given the distance between them. What's the size of the gravitational force? That's as bad as it gets for that. And then just sometimes you'll need to know that the weight is the mass of an object times gravitational acceleration. You take the mass, multiply by 9.8, that gives you the weight. So that one's actually even more important than the law of gravitation in this bit. Tension, not really an emphasis. Normal force, just that it ends up being whatever it needs to be for the object to move the way it's moving. By that I mean, if the object's not moving vertically and the only forces acting on it are normal force and weight, that's when they do balance. If we've got additional forces acting, the normal force is a little bit greater than the weight because of that additional force. If we're accelerating, the normal force has got to change to cause that acceleration. So it's not something that has its own equation. It's something you find as a result of applying Newton's second law, filling out this table, saying whether the net force in the X and Y directions is equal to 0 or not, and then you can solve for normal force. So this stuff, critical, but just having a sense of when normal force is equal to the weight of something, when it's less, when it's greater, that kind of thing is good for concepts. And then friction is not on this exam. So that's main points for chapter 4. Questions? If there's questions on specific practice problems, then we can start with that.
Can we do problem number 10?
In which chapter? This one?
Right there. Mhm.
So use the component method of vector addition to find the components of the resultant of the 4 displacements shown in the figure. The magnitudes are these 4 things, and those are our directions. So this one, it looks weird because all of the vectors are coming from the origin, meaning all their tails are lined up with each other. And so if I were to go about this kind of lay it out as a path you follow thing, I have to slide some vectors around. I'll start before I do that by saying we could fill out this table over here with A, B, C, D without actually knowing what our final vector is going to look like. It just helps to make sure that what we get for the resultant vector of all those makes sense. And so if you had something like this, would not need to slide your vectors around, and more than likely you're given them more like this, where you can kind of draw it out as a trip, or like the sailboat one. You can think of what trip is being. But anyway, same process applies when they're drawn like this. So let me show you the way I would do it if I'm doing the tail to head thing. That would mean, okay, I add A followed by B. So I lay B tail to head with A, followed by C. So I need to lay C tail to head with B, and then followed by D. So I need to lay D tail to head with C. So I'm expecting to get a resultant vector that looks something like this. Points from the tail of the first to the head of the last, or think of it as the shortcut I could take to get to that final location. Alternatively, just so you could see that this is an option, I could use the parallelogram way of combining vectors. I'll do that in green. But then I do need to take them two at a time. So first I find, okay, what is A plus B? I need to draw my parallelogram to those. It's going to look something like that. And then I can take that A plus B vector, add it with C using parallelogram. So A plus B plus C looks something like that. And then I can take C plus D and draw a, let's see, that parallelogram is going to look pretty rough. Let's see if we can do it. I need to draw a vector parallel to this A plus B plus C1. Let me draw it a little bit straighter. Sorry. So I need to draw another kind of D length parallel line. Parallelogram. And if I do that and I had drawn everything exactly to scale, then I should get a resultant vector that points in the exact same direction, has the exact same length as this one I drew using the tail to head way. Looks like I didn't draw something quite to scale, so it's a little bit off. But at the end of the day, it's just about getting a general sense of which way my vector is going to point. So if I had drawn everything absolutely perfectly lengthwise, I would get that. The benefit of doing tail to head is that I don't have to be quite as careful. So I'm going to backtrack and just leave this with the that I did first. Okay, so I need to find my X and Y components of each of these vectors so I can add them together to get the X and Y components of my resultant vector. So the X is the Y. Tell me about the X and Y components of vector A. Are they going to be positive or negative? And this can be anyone. Anyone can answer, but I do want an answer.
Positive.
Is it, could you repeat that?
Positive.
Yep, so positive for X, positive for Y. And that's because if I look at my drawing, A points to the right, up. I could either draw my components like that, or I could draw this one and then up. Call that my vertical component. I'll go with the triangle way because it seems like that's been the way that's clicking better. So let me keep doing that for B, C, and D, just the signs of them, and then we'll come back and find the numbers. Okay, so B, tell me about its components.
Positive, then negative.
Yep. I can see that in my picture because B goes to the right. It goes down. Okay, what about C?
Positive, then negative.
It's because C also goes to the right and down. Okay, and then someone tell me about D.
Negative and positive.
Negative, positive. So it goes left. So the reason I add whatever I get down the columns, I'm going to add what I get in that column, I'm going to add what I get in that column, is that if I look at the X pieces of these, that's one column. I put those all together, I'm going to get the overall X component of my resultant vector or total displacement. It goes right down. If I put those four circled vectors together, that's going to give me this line. I do that by adding everything in the first column. If I put all four vertical vectors together, green for that, that's going to give me this length, my vertical component of my resultant vector. So now we just need to find the lengths of those horizontal and vertical pieces. And yes, it is kind of rough for this one, but backtrack so I have some things. This is like an extreme case of this sort of problem. So if you can do this one, you can do any that I could throw at you on an actual exam. All right. So now we need to find the X component length for A, and then for B, and for C, and so on and so forth. It's going to help me to put these angles back in. So B makes an angle of 20 degrees with the horizontal. I'm getting that from down below where my original B vector was. For C, it makes an angle of 36 degrees with the vertical. So that's 36 degrees. And then D, it makes an angle of 36 degrees with the horizontal. That's 36 degrees. So now we can start kind of filling in stuff. This is AX, AY, BX, BY, CX, CY, BX, BY. So how can I find AX? Let's not leave. I'm sorry, who was it answering me before?
Me,
What was your name? Sorry.
Corey.
Corey. Okay, let's not leave Corey hanging. Let's help Corey out. This is not an easy thing to think about all on your own. So if I know that the length of this vector, the length of vector A, is 2.25 centimeters, then how can I find AX and AY when this is telling me is 60 degrees?
AX over the 2.25.
Is equal to so AX is adjacent to the 60-degree angle, so I could use
Cosine.
So cosine of 60 degrees is AX over 2.25 centimeters. And so AX is 2.25 centimeters times cosine of 60. That's what's going to go in this first bit. That's the X component of vector A. AY is going to be, and this is how I'm going to do the rest of these just to speed it along a little bit. I'll call this one number 1, 2, 3, 4, 5, 6, 7, 8. So when I'm labeling each of these is telling you where it's going to go in our table. And then I'll let you do the math to check that I got this right later on. Okay, so AY, what is AY going to be? y is opposite the 60-degree angle. So I should
This
be,
is sine. I don't know how to pronounce it. Yeah, sine.
yeah, so I would get this by saying sine of 60 is ay over 2.25, and then I rearrange to get ay on its own. I'm just jumping ahead a little bit just for time and for space in this case. It's a little bit limited here. So that's going to go in number 2. Ex. So my b vector has a length of 6.35 centimeters. And I want to find the horizontal component. What's that going to be?
Tangent.
So when I'm looking at my picture here, I see this right triangle where I have right down and then the diagonal. And so in this right triangle, what is bx to that 20-degree angle? Is it adjacent, opposite, hypotenuse? What's it going to be?
Right angle. Is it opposite?
So this one is touching my 20-degree angle.
Oh,
So
20. Okay.
and then I don't know the opposite side. I do know the hypotenuse. So I probably don't want to use tangent. I want to use something else.
Cosine.
Cosine, because that's going to combine adjacent and hypotenuse. So if I do that, it's going to be 6.35 centimeters cosine of 20 degrees. And I'm not worrying about that it's 20 degrees below the horizontal or above because I already accounted for directions of stuff in my SIGN signs over in my table. Y is going to be opposite that 20-degree angle. So we use sine. These are 3 and 4. CX and CY. If I go over to my CX and CY picture, I notice I've got a little bit of a problem because my two components are on one side of my C vector, the blue vector, but my angle that I was given is on the other side. So either I realize, and it's going to help if I kind of break this out on its own. It's 36 degrees. Either I realize that these two sides, CX and CY, are also, it's going to be the same length as this side and this side. It's also CX and CY. Or I could use that this is 36 degrees, and so know that it's going to have to add up with this angle over here to give 90 degrees. And so it would be 54 degrees for that angle. And now I've got a triangle, the one on the right side of this, that has an angle internal to it instead of outside. So I have two different choices here of what I could do. Or I could even, come down here, realize that this is going to be 36 degrees. But I need to have angles that are inside the triangle I want to use sine, cosine, and tangent for. Is there a question on that? Okay. So, Corey, which one do you like best? Which angle do you want to use? Which of these
Say
two?
the red.
All right. So in my red one, where I had to like move around my two components, in this red one, I've got CX over here, CY over here, and then my magnitude, which we were told is 5.47. Hope y'all aren't seeing this Zoom thing pop up a little because it is irritating me. and this is 36 degrees. For this triangle, how can I find CX?
What is I thought the CY was supposed to be where the CX was.
Oh, nope, you're right. My mistake. Okay, now how can I find CX?
Code. I want to say cosine.
Okay, so in this picture, CX is opposite my angle. I have to go across to get to CX. And then CY is the one that's touching that angle. So it's adjacent. So if I say cosine of 36 degrees, that's going to be adjacent over hypotenuse. That's what over what?
Oh, CY over 5.47.
Yep. And so in this case, I'm actually finding CY by using cosine.
Uh,
But if I had, say, used this 54-degree angle, then CX would be the one that's adjacent to that angle. And so I could also call this 5.47 cosine, or I'm sorry, we were talking about CY. Let me look at CY. I could call that, it's opposite the 54-degree angle. So I could say it's 5.47 sine of 54 degrees. I'd get the same number as what I got here. Okay. So that is going to go in for CY. And what is CX?
Sine.
So CX, because it's opposite my 36-degree angle, is going to be the 5.47 sine of 36. But you could call it 5.47 cosine of 54 degrees if you wanted to. Because in this triangle, that CX is adjacent. Either one will give you the same answer. So 5.47 sine 36. That's 5 and 6. We're almost there. The light at the end of the tunnel is visible. We got dx and dy. And so I'm looking now at this triangle at the bottom right, consisting of d, dx, dy. This angle is 36 degrees. So how can I find dx in this? If the length, the magnitude of d is 4.19 centimeters.
Cosine?
Yeah, dx is adjacent to that 36-degree angle, so I would use cosine. It's going to be 0.19 cosine 36 degrees. What about dy?
Sine.
Because dy is opposite my 36-degree angle. 4.19 sine 36. Those are 7 and 8 in this table over here. So we've got these things we add in the first column, these things we add in the second. We'll get a certain number down here. That is our x component of my displacement and my y component. So that one, that. So like I said, this is a pretty extreme version of the kind of thing you would do on the exam. You'd get like 2 vectors and ask about adding them together. So a problem 6 is more kind of on par with what would reasonably be expected of for the exam. Problem 10 is just a good, like, you really want to stretch your muscles and try it, you can. Other ones you want me to look at? Anyone else? I'm going to do the problems I'm asked about. So if there's no other problems, then we'll call it a day. But I'm happy to keep going and answering problems that you want me to look at.
Could we do 21?
Okay, so the minimum takeoff speed is 75 meters per second. What minimum acceleration is required as the plane must leave the runway of length 1,050 meters. Assume the plane starts from rest at one end of the runway. So I would also note that it's asking about acceleration and that the plane starts from rest. My first step in this would be to draw a picture. And so I'm going to think of the plane moving along the runway. Like I said, if it doesn't tell you otherwise, it's a good idea to call your origin of your coordinate system the starting point of the problem. And so I'm going to say my origin is this end of the runway where the plane is initially at rest. And then it's going to move horizontally, gaining speed. It's going to end up somewhere over here. Okay, it's a runway. This is really a 1D problem. So I can think about what's going on when the plane is over here versus when it's over at this final state. And are y'all seeing my cursor on your end?
No.
No? Okay. So I'll draw some arrows, but you don't have to like add in all these extra arrows. I'm looking at what's happening on this end of the runway where the plane's just started, and then on this end where it has gained some speed and is about to take off. At this end, I can say 0 time has passed since this problem started, because that's where it started. I don't know how much time has passed as the plane reaches this point over here, because it doesn't tell me. I know how fast the plane is going over here. We call that the initial velocity. It's 0 meters per second. I got that from when the plane starts from rest. The acceleration of the plane is something I don't know, and it's actually asking me to find it. The x position of this, I could call 0 meters because it's starting from the origin. And that's my kinematic variables: time, position, acceleration, velocity. Okay, now I come over here to where the plane has ended up as it's about to leave the runway. It is moved to the right by a distance of 1,050 meters. And so sometimes we call this x0, just as a by the way. My velocity is, it needs to be 75 meters per second for the plane to take off. So these are both positive values because of the direction I chose my axes. My acceleration is still the same here because it's a constant acceleration. It has to be for me to be able to solve this problem. And because it's saying the minimum acceleration, you have variable, you can get away with other accelerations, but the minimum is just having this constant one along the whole track. So I can fill in my table. X, V0, V acceleration time. X here is the displacement. So we could write delta X or X minus X0. The reason we just write X usually is because we start out at 0. And so X minus X0 is always just going to be whatever the final position of the object is. So in this case, that's 1,050 meters. My V0 is 0 meters per second. My final velocity is something I don't know. The acceleration is, or I'm sorry, my final velocity needs to be 75 meters per second. The acceleration is the thing I don't know and want to find. And time is something I don't know, but it's not asking me, so I don't worry about it. So I look at these four things because I'm given three and I want to know the fourth. And I think about which equation is going to tell me about those, which one's going to relate them. So which would that be if I come up here, my cheat sheet? Just as a reminder, I end up knowing final velocity, initial, the distance, and I want to know the acceleration.
So, quick question, does X represent the distance or does it represent the like the final position? Like
That's a good question. So if I come back down here, I called my initial position 0, and my final position is 1,050 meters away from it. But then in that case, what is my displacement, the change in position? It's 1,050 minus 0, so it's also 1,050. What I'm really filling in this part of the table is that displacement, but because I usually set my initial position to 0, it's going to be the same number as my final position. Does that answer the question? I could try and state it a different way.
yes, but we wouldn't, so we just wouldn't like put the like X initial on there, like we wouldn't put X is 0.
No, because what ends up mattering in the kinematic equations is that displacement. So if I come back over here, just to show where that comes up. So one assumption I made to get to these kinematic equations is, or I guess I put it in terms of X minus X0. Okay, I usually end up setting X0 equals 0 because I'm choosing the starting position to be at 0 meters. And so this second term is always going to equal 0. So I might as well just look at what the value of the first term is, which is the final position. But it's also, because the initial is always 0 in these types of problems, it also tells me what the change in position is, what the displacement is. So let's see. Which kinematic equation is going to help me connect these four things? Okay, you need to connect X, initial velocity, final velocity, and acceleration.
Is it Vx squared equals V 0x squared plus 2ax?
So if these subscripts are confusing you, this is the everyone you, not you specifically, Kennedy. Just think of 1D motion always happens along a single axis. So we can ignore that those subscripts are there. But 2D motion is happening along two separate axes, and that's when the subscripts become important to say one of these sets of equations is for the x-axis, one is for the y-axis. So I didn't write the 1D version because they're already given. It's this set for something moving horizontally, and this set for something moving vertically, meaning free fall. But yeah, I agree. It is that one. And so I need to come down here. It's that. B squared equals B0 squared plus 2ax. Need to get acceleration on its own. To do that, I can subtract B0 squared from both sides. B0 or B squared minus B0 squared equals 2ax. And then to get a on its own now, I need to divide by these other two things. So divide by 2x. That's going to give me that my acceleration is v squared minus v0 squared for 2x, which is, if we put 75 in for v, 0 in for v0 squared, or for v0, and then 1050 for x, that'll get us our acceleration. But it is whatever number that comes out. Okay, and that would complete the problem, whatever you get, we'll substitute everything in. What else?
Can we do 33?
33? Sure. One second. Okay, so 33. An eagle is flying due east, carrying a gopher in its talons. The gopher manages to break free at a height of 12 meters. What is the gopher's velocity as it reaches the ground? Ignore air resistance. So we've got an eagle flying. I don't even know what an eagle looks like well enough to do this, but eagle, that's like a flying penguin. That's what we got here. Got a flying penguin holding a little gopher, and it is flying due east at 8.9 meters per second. And the gopher is 12 meters above the ground. What is its velocity as it reaches the ground? So I do need some axes here. I could either choose right below the eagle and gopher, the instant that the eagle lets go. I could choose at the location of the eagle as it lets go. I could choose a totally different place. Just my random decision here is to call it the ground beneath where the eagle is. We could have also called it where the eagle starts out. It's either is fine. That just changes whether you call a displacement positive or negative, right? It went from up here to down here or vice versa. Anyway, the eagle is flying due east. The gopher breaks free. So we want to know, once the gopher is released, what it does when it hits the ground. Its inertia is going to make it continue moving at 8.9 meters per second to the right as it leaves the gopher's talons. Just like if you're in the car, you flip a coin, it's going to keep moving with you, moving with the car, so that it lands right back in your hand. So this gopher will follow an arc until it hits ground. And we just need to think about all the information we have for when the gopher is up at the top and when it's at the bottom. So initially, it only has this horizontal velocity. So that's my x. It doesn't have any vertical because the eagle's only flying due east. My initial position with the coordinate system I chose is that the gopher starts at 0 meters and that it's at this vertical position of 12 meters. The time that has passed since this problem started is 0 seconds at this point. And my acceleration, what's my acceleration of this gopher going to be? Little louder, whoever's answering.
X would it be 0? For
Yep.
AY, it would be -9.
Yes, so AX 0, AY negative 9.8, because that gopher is a projectile, poor thing. All right, when it lands, it's now at some new horizontal position. It doesn't tell me what it is, so I don't know. I do know that it's now on the ground, which in this coordinate system is y equals 0 meters. The time that has passed, I don't know. I do know the gopher's horizontal velocity already. What's it going to be?
8.9.
8.9, because the horizontal velocity of the projectile does not change. Okay. Vy, I don't know, but it's something I will want to know in order to find the magnitude of the gopher's velocity. AX and AY are the same as they were at the start because they're always 0 and negative 9.8. Okay, so I can fill out my tables. In the examples in the notes, I would only use one of the two because I knew which table, horizontal or vertical, I need. But I would recommend just filling in both and then figuring out which one's going to help you the most to solve the problem. So V0x, Vx, Ax, E, Y, V0y, Y, Y, E. My X here is the change in horizontal distance that has occurred. I don't know that change because I don't know my final position. V0x, I do know is positive 8.9 meters per second. I know that Vx is that same number. So acceleration is 0 meters per second squared. I don't know time, but it's not asking me about it. I do know vertical position, or the change in vertical, which I should be a little more careful here. The gopher ended up 12 meters below where it started. So what should I put for my displacement vertically?
Would it be negative 8.9?
Negative 12 meters, and it's because my final vertical position was 0, my initial was 12, so the change is a minus 12, a decrease of 12. My V0y, 0 meters per second. My Vy is the thing I want to know, my Ay is negative 9.8. And then again, don't care about time. So I need to find Vx and Vy, but just through knowing how projectiles work, Vx is done. Now I just got to find Vy. So I should use my vertical information to do that. I have these three things, y, v0, y, and ay. I want to find Vy. Which equation is going to help me do that?
Would it be the Vy equals V0 plus 2A X and Y?
So let's see, this one right here,
Yeah.
second one, yes, yep. There he is. So Vy squared equals V0y squared plus 2y times y. And so My Vy is already on its own. I just need to take a square root of everything to get it. So Vy square root of V0y squared is 2ay y. And so if I put in negative 9.8 for that, first for ay, make that arrow point better. And then V0, that whole thing is going to be 0, and then y is negative 12 meters. And I take a square root of it. That'll tell me my vertical component. And I'll know, based on this situation, what's happened, that it should be, for one, the gopher maintains that horizontal velocity, but for two, it has a downward vertical velocity because it's been falling. And so I'm going to take the negative of whatever I get here. When you take a square root, you have a positive and a negative root. I take the negative because I know the gopher is falling downward when it reaches the ground. And so if I put that in, I'll get my Vy component. And then I can find the magnitude of the velocity, which is, right, I have my two pieces of it. I have Vx, Vy. I put them together to get my overall velocity, V. I can find the magnitude of that or the speed of the gopher with the Pythagorean theorem. That's my magnitude of that vector. And I put in all the numbers, I should get to that. Okay, I think I have time for one more like calculation question or maybe a couple more concept questions. And then I need to get going.
Can you go back to 21 right quick?
What about 21?
I just didn't write all the information down yet.
In the meantime, does someone else have another question you want to look at? Maybe chapter 4, because we haven't looked at anything in chapter 4.
Can we do question 51?
Okay. All right, just let me know when you've got 21 down, and then we'll move to that.
I got it down.
Okay. 51. Man holds the end of a massless rope. At the center of the rope, a 7.9 kilogram ball is shown. What is the tension in the rope if theta is 6 degrees? So that's 6 degrees, 6 degrees. And I've got this rope on one end and rope on the other. So that rope is going to exert a force of tension on this ball along its length. That's going to pull this way. I'm going to call that T2 because it's also going to be pulling this way, T1. Okay. If you think about, you put your finger on a rope and someone pulls in both directions, you're going to feel that pull in both directions. Or if you just have a really taut rope, one that's like really straightened out and you press on it, you're going to feel the rope push back outward, back upward. Okay, so those two forces act. And then the ball has a certain weight to it. And I'm going to be able to calculate that if I know the mass of the ball and I know the gravitational acceleration. Zoom is wigging out. Anyway, I take that, and now that I'm done labeling all my forces, I turn it into a free body diagram. And I need to choose my axes that I'm gonna break stuff into components along. I just want to draw the P1 a bit straighter. You choose my axes. There's not really a good choice in the sense of any axes I draw are going to leave at least two vectors off of them. So I'll need components for two vectors. So I'll just do the usual vertical and horizontal axes. So I have two angles I could work with. I could work with this one over here, or I could work with the other complementary angle. If I go to my picture, I see that this one is the one that I drew in my free body diagram over here. That one is going to be theta because of that alternate interior angles of parallel lines thing, or because if I draw this right triangle in, this angle is going to be 90 minus theta, so that all three angles in this triangle I just drew in add up to 180. And that's going to mean that that 90 minus theta angle is going to have to add with the angle I drew down here to give 90 degrees. And so the angle I drew is theta itself. So these angles are theta, 6 degrees. Right, I'm going to need my components of the tension, pulls to the left, up. And this one, T2, pulls to the right and up. And now I have the information I need to fill in my. You may notice I haven't even looked at what it's asking me to find in problems like these, because this part, you do the same every single time. If there's not a picture given, draw one, label your forces, draw a free body diagram from that, break stuff into components along your axes, and then fill out your table. All that's always the same. So in this particular problem, I've got C1, C2, weight. Tell me about my weight vector. What are its components?
Oh, would it be 0? Since it,
X.
yeah, since it don't have it don't go left or right. And would it be negative? I think just negative weight.
Yep, negative W, because I don't know the size of that weight vector at this point, but I actually could find it. It's negative the mass of the ball times gravitational acceleration, 9.8. If you're wondering, do I put a negative here for the 9.8? No, because really it's saying that the weight acts in the direction of gravitational acceleration. I'm just scaling that vector up by this 7.9 kilogram mass. And so the negative here is the negative that you're thinking should go in front of the 9.8. It's already accounted for in that we accounted for the weight being downward. Okay, and so that's going to be negative whatever that comes out to. And then tension. Help me out with tension. Let's start with T1. My X component. How can I write it in terms of T1?
Would be
Would
negative.
it be, oh,
Oh, you go ahead. You go ahead. You go ahead.
would it be negative cosine of theta?
Yep, so it's negative because T1X points to the left. And then I look at my triangle here. It's made up of T1x, T1y, and the T1 vector itself. That's a rough triangle. But anyway, so yes, T1x is adjacent to that theta angle right there, 6 degrees in this case. And so I would use cosine. It's going to be T1 cosine of theta. Okay, what about y, my y component?
Positive T1 sine.
Yep. Okay, and then T2 should be pretty quick.
T2 positive T2x cosine.
Mhm.
And positive T2 sine.
I agree. So we've filled out our table. That's going to tell us about our net force components along each axis, the x and y axes. If I sum down this column, that tells me about my net force in the x direction. I like to put positives first. T2 cosine theta minus T1 cosine theta. And then if I sum down this one, it's going to tell me my net force in the y direction. That's going to be T1 sine theta plus T2 sine theta minus whatever this number came out to be. I'll just leave it as minus mg for now. You could put that number in now. I don't know what it's going to be. Maybe it'll be around 80. Anyway, once we do that, this is my net force in the x direction. This is my net force in the y direction. And so I say net force in the x direction is equal to mass times acceleration in the x direction, or T2 cosine theta plus T1 cosine theta equal to the mass of the ball times its acceleration in the x direction. The y is going to be equal to mass times acceleration in the y direction. So theta plus T sine theta is mg equals mass times acceleration in the y direction. Now we need to decide, is the ball accelerating in the x and y directions? So is it accelerating in the x direction? What's that ball do?
It's decreasing. Wait, in the extra.
This guy's just holding a rope. The ball's sitting on the rope, just hanging there. Okay. So if it's just sitting in place, just hanging, what can we say about its acceleration in the horizontal direction? Meaning what it's doing left or right? Is it accelerating? Is it gaining or losing velocity?
It's not
Um,
accelerating.
It's not. So I can say this side is equal to 0. Right? What about my y acceleration? What the ball is doing up or down?
Down.
Okay. Is the ball speeding up or slowing down though? Or is it just sitting in place because of this balancing of stuff that's going on? Just picture yourself holding two ends of a rope and you have something hung in the middle of it and you're just holding the two ends.
Just be sitting in place.
Yeah, sitting in place. So tell me about its y acceleration.
It's 0.
0. Remember, acceleration is telling you how the velocity of that ball is changing along each axis. If it's just sitting in place, its velocity is not changing. So its acceleration is 0. Okay. Now, I have two equations. My only two unknowns are T1 and T2 because I know my angle theta and I know the mass of this ball. So I can solve them for T1 and T2. It's actually not that bad in this case because this equation is just T2 cosine theta minus T1 cosine theta equals 0. Or T2 cosine theta equals T1 cosine theta. Or I can cancel cosine theta from both sides. T2 equals T1. That's saying that if you hold the ball just like this, where the angle that the rope makes on either side is the same, the tension in both ends of the rope is the same. And so that's what that tells us. Now I need to find the actual number, and I can do that by going over here. I can use the fact that T1 equals T2 to substitute in for either of those. I'll put T1 sine theta plus for T2, it is equal to T1, so I put that there. Minus mg equals 0. And so this is 2 T1 sine theta. Equals 0. And so if I solve for T1, I add g to both sides, 2 T1 sine theta equals mg, then divide by everything that's not T1 to get it on its own. So 2 sine theta. That gets me to T1 equals mg over 2 sine theta. And I know my mass of the ball. I know g is 9.8. I know my angle theta is 6 degrees. So I have everything I need to find T1, and then I just know T2 is exactly the same number. So questions on that one?
Yes.
Oh, sorry. You go ahead.
Where did you get the 2 in front of T? Like I'm confused about that.
So if we backtrack to where I added up all of my different forces, I had T1 sine theta and T2 sine theta. Okay, that's how I ended up with this equation right here. But I found out from my x components that T1 and T2 are equal to each other. They're the same number. And so if I put that in to this equation over here on the right, that lets me say, okay, instead of T2 sine theta, I can write that term as T1 sine theta, because then I only have one variable, T1, instead of both, right? I don't know how to solve one equation for two different variables. So by doing that, I end up with this T1 sine theta that was there originally, and then this one right here that came from replacing T2 with T1. So I have two of these T1 sine theta things. I have two T1 sine theta. I'm just adding those two together. If it makes more sense another way, I can say T1 sine theta plus T1 sine theta is something that I can factor, say T1, or let's say I can factor the sine theta out of both, pull it out of both. And I have T1 plus T1. All right, that's two of those things added together. That's 2 T1 and multiplied by sine theta. So that's how I get 2 T1 sine theta.
Okay.
Right. Other questions? I don't think I can do a whole other problem, but are there other questions about this particular one? It sounded like there was.
Okay, I had a question. So for T1, that's gonna be our final result, like final answer.
Yeah, so this, whatever number we get from this is that tension. It asks about both.
Mhm.
Really, it's the same rope, and so it's gonna be the same number, but you end up getting T1 and T2 are the same number.
Okay, so it would be the same answer for T2.
Yes.
Okay, all right. Thank you.
I have a question. So would this problem be on the exam, or would it be more conceptual question?
A problem like this where something is at rest, and you have to add up all the forces and find something, yeah, for sure, it could be on.
Okay.
I usually try to account for that math like this can be a little tricky, both in how I grade and in which problems I specifically choose for the exam. But again, if you can do the harder problems on the practice, the exam itself should not be that bad. Any final questions?
How many questions will be on the exam?
Say again?
How many questions are going to be on the exam?
I'm shooting for, I think I said 10 to 12 at first. It may shoot into the 12 to 14 range, but by that I mean like 7 or 8 conceptual questions and like 4 to 6 calculation questions. And for me, a question like maybe this one with the eagle, it might be actually broken up into about 2 to 3 questions to help lead you through the problem a little bit more. So
Oh,
that's how it ends up being more like 12 to 14. It's just that I break some problems into 2 or 3 pieces so that you just have to do a little bit at a time.
okay.
And then you said that we can also bring a sheet with us for the exam. Is that correct? Or
Yes, you can have the front of an 8.5 by 11 sheet of paper with whatever you want on it. If you find an old exam of mine and you copy down every bit of it, I'm not going to say that that's fine too, because it's about just applying what you have learned to different problems.
okay.
It doesn't have to be just formulas.
Nope, it can be absolutely whatever you want.
And you said a front of a sheet of paper like that. That's like
Yep,
the length.
sheet of notebook paper, whatever you can fit on it. I've had people print a piece of copy paper before. I've had them write as small as they could. I've seen a lot of different things. It's whatever works best for you and how you approach these problems and how you study. Maybe one final thing I'll say is that if you are looking to see more problems worked out, there is on Wiley, if you go to Wiley course resources on the left, and then look for videos of problems being solved, or if you go into any module and look for chalkboard videos, I think it's called chalkboard and additional videos. That has additional problems being solved, and then the reference sections for each chapter. It says reference chapter 1, reference chapter 2, and so on, that appear under each module have additional worked practice problems. Okay. So the way to prepare is just keep doing practice problems, see if you get the right answer. If you don't, look back at how you approached it and see if you can figure out where you made the mistake, and rinse and repeat until you get the right answer. You learn a lot just from doing that. If there is no more, I will call it a day. And this will be posted in a few hours while YouTube processes it. And if there are any additional questions, you can email me. I'll get back to you as I can. I'm in about the same boat as you as far as sleep goes. I've gotten 3 or 4 hours for the past week, so I may be asleep for the next little bit, but that'll be while the video is uploading. And then I'll let you know. I'll send out an email when it's posted.
All right.
Everyone have a good day, and again, reach out if you have any questions.
You too.
Thank you.
Thank you.